So, if you recall, we wrote this equation as m dv dt is equal to mg minus mkv, no vector here. Now, here the drag force has been taken as force per unit mass. If we do not take this drag force as unit force per unit mass, what do we get? We simply have m here. So, the equation becomes dv dt is equal to g minus k by mv. And the trick I taught you very recently is to set this equal to 0 in order to get terminal velocity, and we get a terminal velocity to be equal to g by gm by k by setting dv dt equal to 0. Also, if we solve this full equation, we get an expression of v to be equal to the power minus k by m t. So, you see, not only the terminal velocity is modified. Now, if we write this as Vt 1 minus e to the power minus t by t0, we see that Vt becomes mg by k and t0 becomes m by k. So, it is the same result as we got from the previous set of equation, only k is replaced by k by m. And also note that when we have t0 is equal to 1 by k, that means the unit of k is given as second inverse. When I have t0 is equal to m by k, the unit of k is given by some kg or gram, maybe kg, second inverse. So, depending on if the data is given in second inverse or kg per second inverse, we have to use one of these two equations accordingly. So, in one case we have to use Vt equal to mg by k and t0 equal to m by k, and the other case we have to use Vt equal to g by k, t0 equal to 1 by k, and this is if the initial force is given as minus kv, and this is if the initial force is given as minus m k v. Okay. The final equation becomes same. Only thing, the value of Vt and T0 will change. Okay. Now, there is another type of very important, there is a very important application for this type of equations, and we will discuss one such application, which is called the falling ball viscometry. That is used as a laboratory experiment. Also in industry, people use it a lot in order to measure viscosity of a fluid. Okay. So, how does it work? Let us assume there is a column of viscous liquid. So, there is some viscous liquid, okay, and what do? We drop a small metallic sphere of mass m and radius r in this column of liquid. Okay. Now, what happens is, as it starts falling through, because of this there is a viscous drag present, it essentially attains a terminal velocity. Now, in order to gain a more mathematical insight, let us try to see what are the forces acting on this particular thing. Okay. Of course, there is a force downwards which is due to its mass. Secondly, there is a force which acts upwards due to the buoyancy. We all know buoyancy, right? Buoyancy is the force applied by the liquid displaced by this particular body, and of course there is a viscous drag force. So, if we write the downwards forces, this is simply mg, and upward forces, one is the buoyancy and the other one is viscous drag. We call this one as Fb and this one as Fr. Okay. So, if we write the force equation, which will be m dv dt is equal to mg minus Fb minus Fr. Okay. Now, what are the expression for this buoyancy forces and viscous drag? Buoyancy force, the expression is pretty straightforward, we all know it. Buoyancy force will be the volume of this particular object multiplied by the this one, the density of this liquid. So, Fb will be 4/3 pi r cubed rho. So, let us assume rho is the viscosity of this liquid. Similarly, we can write m, which is the mass of this small metallic ball, as 4/3 pi r cubed sigma. Sigma being the, so rho is the viscosity, sorry, rho is the density of liquid, sigma is the density of solid, this solid, the material of this ball. Okay. It could be a steel ball, could be a any other hard sphere. And we also introduce or not introduce, you probably know that there is a viscosity. So, it is the viscosity, eta we call the viscosity of liquid. Okay. Now, where does this eta come in? Eta comes into this term. There are theories which tells you that Fr will be 6 pi eta r v, v being the instantaneous velocity of this ball. Okay. Ball is falling with a velocity v, 6 pi is a constant, r is the radius and eta is the viscosity, and this is the equation of viscous drag according to Stokes law. Okay. So, the viscous drag is determined by Stokes law and there is an expression for it. Please remember, this expression is valid only for spherical object, and it is also a very idealistic equation. In reality, this 6 pi eta is, 6 pi is not a 6 pi, it generally there is a correction term associated with it, but let us not go into all these technical details. Let us keep it simple, and if we now plug in this expression for Fb, Fr and m in the left hand side. So, essentially what we are planning to do is we are trying to get an expression for the terminal velocity for this particular case. So, what happens is, for terminal velocity once again we set dv dt equal to 0. So, the left hand side becomes 0. Now, if we do that and we put Vt for V, because we are setting dv dt equal to 0. So, this equation becomes m. Okay, so m will be 4/3 pi r cubed sigma g minus 4/3 pi r cubed rho minus 6 pi eta r v t equal to 0. Okay. Now, once we simplify this, we get an expression for v t, which is 2/9, it will be 2/9 g. G r square sigma minus rho divided by eta. Okay. So, we have an expression for the terminal velocity here, but that is not it. So, that essentially what we are planning to do is we are trying to estimate eta from this experiment. So, what happens is, in reality there will be a marking in this on this tube, which is separated by a distance L. Okay. Now, there will be one camera here and one camera here. Okay. So, once the ball starts falling, of course, it will have sufficient length on this marking, so that by the time it reaches here, it falls, it gains the terminal velocity. Please remember, this experiment will not be a valid experiment unless and until this sphere gets to its terminal velocity. Assuming that we have enough length for the sphere to travel, by the time it reaches here, it reaches the terminal velocity. What we can do is, we can take two snapshots of this sphere passing this point and this point, which is separated by a distance L, and then we can calculate the time t for which it took in order to reach from this point to this point, and then your v t will simply be L by t, isn't it? So, using these two cameras, we measured the time and we already know the distance L. So, we get v t equal to L by t, and when we plug it back in here, we get eta will be 2/9 g r square sigma minus rho times t by L. Okay. Out of this expression, 2/9 is a constant which has a fixed value. L we know, G we know, R we know a priori, sigma and rho also we know. All we need to do is we need to calculate this t, or we need to measure this t accurately enough, and essentially we have to give we have to, if I can measure the value of t, we can immediately get a value for eta. And this whole setup is called, there is a name for it. It is called the falling ball viscometer. Okay. So, it is called a falling ball viscometer, which is a, so I will write it again, I think probably you won't see it properly, I will just write it here. Falling ball viscometer. Okay. So, it is a very simple experimental setup, but which is pretty accurate. People use it in their laboratories in order to get a better, I mean first order approximation or first order estimate of this viscosity viscosity eta of the fluid. Also in industry people use it a lot. Okay. So, now with this I just want to give you one more set of information, which is pressure drag. Okay. Now, viscous drag, the expression for viscous drag was F is equal to 6 pi eta r v. Now, this is valid for a very regular shaped object which is moving slowly enough inside the fluid. The v has to be very small, I mean not very small, but there are certain limits put on v in terms of the Reynolds number, and I am not going into the details of that. But as a thumb rule, we can assume that if it is a well shaped small object moving with a limited speed, then we can assume that this Stokes law is a good approximation of the drag on this particular on this object, and we call it the viscous drag. But when the velocity becomes higher and higher, then we essentially enter into the regime of turbulence flow, and there we have an expression. So, we call it Fv, this is for viscous drag, and we have a pressure drag which is half C rho A v square, rho being the density of the liquid, A is the cross section of the object which is moving, the effective cross section, and C is something called a shape factor which is related to the geometrical shape of the object. But let us not go into all the details, but what is more important is this V square. Okay. So, essentially we can represent this force in our equation as minus k V square. So, in certain occasions you might see in the problems or in certain books that in some of the treatment force, the resistive force has also been taken as minus k V square, and you will immediately know that this is also nothing. So, why I am trying to tell you this, because you need to know that this is not something very impractical, it is just that people are working in the pressure drag regime. Okay. So, let us not go into the details of these things, and let us try to solve some problems. Okay. First problem, we have two problems for today's class. First problem is a motor car is driven with a constant force F at all speed, meets with the air resistance proportional to the square of the velocity. If u is the maximum speed of the car, show that its acceleration varies as u square minus v square at a speed v. Okay. So, here the force with which the car is driven is a constant force, and it is given as F. So, if we write the equation of motion, it will be m dv dt equal to F minus k v. Okay. K v because k v square. So, because k is the proportionality constant, because it is given that the resistive force is proportional to the square of the velocity. Again, please remember that because motor car is an object which moves relatively faster compared to a raindrop falling raindrop or a sphere falling in the viscometer. Motor car has a much higher velocity. That is why we are working in the pressure drag regime, and we have the viscous or the force, resistive force as minus k v square. Okay. Now, if u is the maximum velocity possible, now understand this situation. Let us say this is our motor car, okay, and it is moving under the influence of a constant force F, which is in this direction. Okay, it comes from its engine. Now, air resistance will try to slow it down, and essentially these two forces will combat. And so what happens is, because this force F is a constant, okay, we have to, at some point we will reach a maximum force u, maximum velocity u, beyond which the car cannot move, and that u will be reached if dv dt equal to 0. Now, when this happens, we immediately see that if dv dt is equal to 0, then f minus k u square is equal to 0, okay? And that essentially means k is equal to, or rather f is equal to k u square, okay? Now, if we move back to the original equation and put this expression for f over here, we see that our equation becomes m dv dt equal to k u square minus v square, or dv dt is equal to k by m u square minus v square, okay? So, we got our desired result. This is our acceleration, which is proportional to u square minus v square at all speed v with the proportionality constant k by m. Fine. So, we have solved this problem. Let us move to the next problem. The next problem is a paratrooper falling from rest and acquires a limiting speed of 24 kilometers per hour. Assuming that the air resistance is proportional to the instantaneous speed, determine how long it took to reach the terminal velocity. Okay. So, in order to solve this problem, we immediately recall that v is given as Vt 1 minus e to the power minus t by t0, right? That was the expression we used, irrespective of whether we took kV for the force or minus kV for the force or minus mkV for the force. That was the final expression. Only thing is Vt and T0 will have slightly different form. Okay. Now, it is given that Vt is equal to 24 kilometer per hour, which will essentially reduce to 24,000 by 3600 meter per second to 3. So, it will be 20 by 3 meter per second. So, this is our terminal velocity. Okay. Now, what we need to find out essentially is 5 T0. As I have discussed just some time back, that 5 T0 is the time taken to reach Vt. Okay. So, if we assume this particular expression, that Vt equal to g by k, in that case T0 will be simply equal to 1 by k, and if we take Gt equal to Vt equal to gm by k, so this will be equal to m by k. Okay. So, all we need to do is we need to calculate this k or k by m, whichever way you prefer it. It will essentially give you the same answer. Okay. Let us do it with simply k, because it will look better, nothing else. Okay. We know that g is equal to 10 meter. Okay, we are assuming that g is equal to 10 meter per second square. It could be 9.8 meter per second square, but just for simplicity I am taking 10 meters per second square. So, that will give you k equal to, this is 20 by 3. Okay. So, it will be 10 divided by 20 into 3 second inverse. So, essentially it will be 3/2 second inverse. Okay. And we need to compute 5 T0. So, 5 T0 is equal to T0. So, that means T0 is equal to 1 by k, 5 T0 is 5 by k, which will be 5 into 2 by 3 second, which will be 10 by 3 seconds equal to 3.33 seconds. So, the final answer is 3.33 seconds. A paratrooper who reaches a terminal velocity of 24 kilometers per hour, it takes 3.33 seconds to reach the terminal velocity. So, immediately know that although it looks, I mean, it is not that straightforward, because this viscous drag is not a very straightforward phenomena. Sometimes we have a more, critical expression for the terminal velocity. We are working on a very simplistic model here. Please remember, always remember that the actual physical situation could be lot more complicated. We are just assuming that there is no, flow in the air and there is no turbulence in the air, which is not true. There is a flow, there is a turbulence. So, all these terms it comes into account. But even without considering all this, we immediately see that it is a very short time. Okay, it might take little longer, might take even shorter, but almost immediately after opening of the parachute, a paratrooper reaches the terminal velocity, and that is why even after landing from a distance of a height of sometimes tens of kilometers, they do not break their bones. Okay, fine. So, this is essentially it, and also I would like to touch upon one particular topic, which is a projectile motion under air resistance. I will not go into the mathematical details of this, because this is slightly too complicated and it is probably not needed at this level, but I will just give you a very basic brief description of what happens. So, what happens when we fire a projectile? Let us say there is no air resistance, nothing, and we all know that projectile essentially takes a parabolic path, okay, and the range of this projectile, this is called the range of this projectile, depends on the initial velocity v0 and the angle theta. We all know that, and we have all solved, and we know that by optimization of this range we get theta equal to 45 degrees is the optimal angle for which the projectile will have maximum of range. Okay. Now, what happens is, in case there is air resistance present, what happens is a projectile will fall short of its desired range. And what is more important is, if we fired the, so all these things can be solved mathematically, but I am not going into the, as I said, I am not going into the details of the equation. What I am more concerned about, to give you a overall description, physical description of what happens. What is very important is, if we fire the projectile higher, as in if the angle theta is somewhere in the range of 60 or 70 degree, the effect will be more prominent. Let us say for 60 degree, if this is the desired range, then with air resistance it will fall much shorter. But whereas if we fire the projectile at an angle of 20 degree, if this is the range, with air resistance the range will hardly change. What I am trying to tell you is, as we go higher and higher up in this angle, the effect of air resistance is more and more on the projectile range, and that is very quantitatively understood, because as we reach higher, there are more scope of this particular object which is falling to reach terminal velocity. If we are not reaching high enough, the terminal velocity might not be reached. Now, all these things can be looked upon mathematically, more mathematically, but we are not going into this. So, with this discussion we are closing the topic of motion in resistive medium. Next class onwards, what we are going to do is, we are taking up the problem of variable mass. Thank you.